Today's topic in thermodynamics is various process. There are basically four processes. First process is isothermal process. Isothermal process. In thermodynamics, we have almost 3 to 4 parameters. PVT, pressure, volume and temperature are basically three main thermodynamical state variables. Okay. Then first processor is isothermal. Second is isochoric process. Third is isobaric process. And the last and very important process is adiabatic process. Adiabatic process is very important process. These four processes are varying with these thermodynamical variables like that. First isothermal process, we have only one state variable at constant. Temperature is at constant. The temperature variation does not observe in isothermal process. And the next is isobaric. In isobaric process, we have volume. Volume state variable as a constant. No variation in volume. And in third isobaric process, we have pressure state variable at constant. And at the last, in adiabatic process, these three variables can be varied, but another variable, another state variable like heat. Q is a heat. Heat exchange in the system is always at constant. Even varying pressure, volume and temperature can be varied, but heat is constant. We can study all four processes parallelly. Like one variable who is constant, then the change in this variable will not be observed. Okay. And volume dV is equals to 0. Pressure constant there, that means change in pressure is observed. No observation in change pressure. And heat is a constant, then the change in heat is 0. Along these parameters, we can derive the state equation of these four processes. Like we have here a ideal gas equation here. For an example, we can solve it here. Ideal gas equation, PV is equals to nRT. Pressure, volume and temperature variable are related by these ideal gas equation, in which n is the number of moles, r is the gas constant, and here for isothermal process, when temperature is also constant, then constant into constant into constant is equal to, first PV is equal to totally constant. Then constant को आप K consider कर लीजिए, K is considered as a constant, then PV is equals to constant is the state equation of isothermal process. Then we can write here state equation. Even state equation is also called equation of motion of that process. So then PV is equals to K, constant is the state equation. According to this equation, pressure is equals to K constant upon volume. Okay. Next, for isochoric process. In isochoric process, we have volume as a constant parameter. Then we can set these equations like this. P is equals to N R. I mean, we can shift it, the constant variable on RHS and the variables are at LHS. T, temperature को इसके नीचे ले आएंगे यहाँ पर, is equals to V. Then these all three symbols are at constant. Then consider as a K. For isochoric process, volume is constant, then constant divided by constant is equal to overall constant. Then P upon T is equals to K constant. Is the state equation for isobaric process. P upon T is equals to K constant. Next, for isobaric process, we have pressure as a constant parameter. Then constant parameter can be shifted at RHS. Then V upon T is equals to NR upon pressure. Constant into constant divided by constant is overall constant variable. Constant parameter. Then V upon T is equals to constant K is the state equation of isobaric process. V upon T is equals to K constant. Then at the last adiabatic process, we don't have any relation like ideal gas equation for Q heat. So isothermal process state equation can be modified for adiabatic process like that. PV for isothermal process, PV is equals to constant, then PV is equals to constant, but adiabatic ratio is included gamma for V raised to the power gamma. So then PV raised to the power gamma is equals to constant is the state equation of adiabatic process. Here we introduce a gamma mu factor. Actually gamma is called adiabatic ratio, also ratio of two specific heat Cp upon Cv. Gamma is equal to in term of two specific heat ratio Cp or Cv. So then we have these four processes with these four state equation, and now our next topic is the graphical representation of all four processes. For all four processes, we have the graph in the state variable, even in the variables for P, V, T also. Then next, first for isothermal process. So first for isothermal process, we have two variables related by this equation. What we see here, that pressure and volume are two state variable. They both are inversely proportional to each other. Then when these are inversely proportional, the variation is shown by hyperbolic in nature. Like P and V have graphs such that decreasing. As we increases volume, then pressure is decreases for isothermal process. And for second process, for isobaric process, from state equation P and T is P divided by T is equals to constant. That means P proportional to temperature. When two variables are proportional from each other, then the variation is shown by a straight line passing through the horizon. Then in third isobaric process, pressure is constant and the state equation is V upon T is equals to K. That means V is directly proportional to temperature. Here also two variables are directly proportional from each other. Then temperature and volume having also straight line relation passing through the horizon. And at the last, for adiabatic process, again pressure and volume are related by these equations, state equation, from which pressure is the volume are shifted here, then 1 upon volume raised to the power gamma. That means again volume and pressure are inversely proportional to each other. Then similar to the isothermal process, for adiabatic process, pressure and volume are hyperbolically related. And what we observe here, then pressure and volume, these two graphs are shown like similarly, but here there is a very even a sharply relation related with slope of these curves. We can discuss it in the next topic. Okay, thank you. Our next topic is the comparison of slope between two process, isothermal process and adiabatic process. The state equation of isothermal process. Isothermal process. What is the state equation? We calculate PV is equals to constant. Is the state equation of isothermal process. And for adiabatic process, state equation is the PV par gamma is equal to constant. We have two equations here and we differentiate both two equations separately. Then first P pressure is the first variable and volume is considered as the second variable. Then differentiate this equation again. First, what is the rule of differentiation? When two variables are multiplied from each other, then differentiate first variable firstly, then dP, and second put it as a constant, then volume is as a constant. Multiply these and then add them. Then first, which are already differentiated, then in this step it is considered as a constant, and the second variable is as a differentiation. Then dV. Constant. RHS is constant and the differentiation of constant is always 0. Then what we do here? dP and dV. तो then हम इसे शिफ्ट कर देंगे. तो dP V वॉल्यूम आगे पुट कर दीजिए is equal to this term is goes here, then minus dV. These and these. dP upon dV is equals to minus P upon V. dP upon dV is the slope of straight curve. What is the straight curve of isothermal process? We have a straight curve between two variable pressure and volume. This is an hyperbolic in nature. But the slope of any curve is dy upon dx, even dP upon dV. dP upon dV is the slope of isothermal process curve. Again, we also apply the similar differentiation for adiabatic process. Again, first variable, second variable. These two are multiplied from each other and differentiate first variable and second is held as a constant. Again, add them similar to this equation. Again, add them. First variable is put it at constant and then differentiate second. Here second variable is V having par gamma. So we apply those formula. When we have x variable raised to the power n, then differentiation of this is n x raised to the power n minus 1. So we apply this formula here. Then V raised to the power gamma having gamma V volume gamma minus 1. Similar to this, and the variable is dV, so dV multiply is equal to constant. Differentiation of constant is again 0. Then we also set this here dP V raised to the power gamma is equal to minus of P. P is the pressure term, gamma is the power term which is constant. Then multiply this here and V raised to the power gamma minus 1. Even we can separate this power into two parts, like V ki power gamma and V ki power minus 1. Minus 1 can be put here. V raised to the power minus 1 is put here and V raised to the power gamma is here. Then dV. Again we can set this as a slope of curve. So dP upon dV is equal to, again calculate them, V raised to the power gamma and V raised to the power gamma cancel from each other. Minus gamma is gamma here, P upon V, then P upon V. So this is also the slope of PV curve in adiabatic process. So in adiabatic process. Here we can compare these two slopes. This is the comparison process in which dp upon dv slope of the PV curve is minus p upon v, again minus p upon v. But in diabatic process, slope is gamma time greater than to isothermal process slope. So we can draw it even in a similar manner of hyperbolic nature. For an isothermal process, for a diabatic process, if these two processes are combined from each other as a graphical in nature, then we have this curve like that. This is for a diabatic process having slope gamma time greater than from the isothermal process, and this can be for isothermal process. So this curve shows the comparison of slope of these two processes. Thank you. Topic is the work done in 4 processes. First we calculate the work done in a diabatic process. In a diabatic process, the formula of work done in thermodynamics is equal to integration of P dV. This is the basic integration term where variable is volume, and here another term, even another state variable, pressure, is here. But for integration we have the same variable here, so we use state equation of adiabatic process. State equation of adiabatic process. What is the state equation? We have P volume into volume raised to the power gamma is equal to constant K. Then we can say pressure in terms of volume like this. This is equation number 2 and this marked as equation number 1. Then put the value from equation 2 into equation number 1. Then W is equal to integration of P dV. Then pressure is equal to K constant upon V raised to the power gamma and dV. Here K is constant and integration is always done by variable term. Then K 1 upon V raised to the power gamma. Then V की power gamma can be shifted in numerator term minus gamma and dV. Now it's time for integration term where volume is the variable. Then what about the limit of integration term? Here this is called always a lower limit and this is called upper limit. Consider volume as initial volume and for upper limit as a final volume. Then what about integration formula? I will set it here. Integration of x raised to the power n dx is equal to always x raised to the power n plus 1 upon n plus 1. It is the basically integration formula. We can apply it here like a. And then limit integration term can be shifted into limit form by this major bracket with lower limit and upper limit as it. Then V raised to the power minus gamma. When we compare these two formulas, these two terms, then in place of small n, here is minus gamma. Then we put it V minus gamma plus 1 upon minus gamma plus 1. Look at this term, minus gamma plus 1, I mean 1 minus gamma is a constant term. Then W is equal to K upon 1 minus gamma. And then what about these limit? When the answer of integration is here, then in place of volume upper limit is Vf and lower limit is Vi. And we can difference, I mean upper limit minus minus lower limit is the answer of this bracket. Vf upper limit, and here minus gamma plus 1 is the power, and minus V. I is the lower limit, and then minus gamma plus 1. So answer is here, but we set it in a proper manner with help of this constant k. We can multiply it here, but because of it is constant, we can use the state equation in another form. Like for initial, this equation can be write as initially Vi raised to the power gamma, and for final also, for final term Pf Vf to the power gamma. Again it is constant and it is also constant. So these two are related by this big bracket. We use this concept here, like k's can multiply with final term also, like k v final raised to the power minus gamma plus 1. Again negative sign is here. K also multiply with this initial term minus gamma plus 1 divided by 1 minus gamma, which is constant. Again k, when we use the final term, then k constant is equal to the final multiplication, and when k is related with initial term, then we put the value of k in term of initial variable. Like k for final, k is equal to Pf Vf. So then Pf Vf raised to the power gamma is equal to k term, and in place of k we put it and multiply by Vf minus gamma plus 1, and again minus is here. Again k constant is related with initial term, so k is equal to initial term Pi Vi raised to the power gamma, and dot multiply by Vi initial term minus gamma plus 1 divided by 1 minus gamma. Here we can solve this common variable, common base. Vf, again Vf is the same base, so we can add these two terms. Minus gamma is here, plus gamma is here, gamma is cancelled from each other, then only Vf raised to the power 1 is remaining here. Pf Vf to power 1. Then again minus Pi is here, Vi raised to the power gamma dot Vi raised to the power minus gamma. Again these two are combined from each other and cancel from each other, then only Vi raised to the power 1 is remaining. So then Vi raised to the power 1 is here. Again 1 minus gamma is the term. So this is the final answer. We can shift it in this identical form where 1 upon gamma minus 1 is here. We can interchange the sign because Pi Vi minus Pf Vf. It is the final formula of work done in adiabatic process. Work done in adiabatic process is related with pressure and volume term, and we can also write it in term of temperature. Temperature is how we can write this. Actually, we can write this by use of ideal gas equation. We know ideal gas equation is PV is equals to nRT. So, for initial term and for final term, we can set it in temperature form as Pi Vi. N is constant number of moles and R is the gas constant, and temperature is Ti, initial temperature. Again for final state, Pf Vf is equals to nR Tf. We put these two equation values in this formula. So W work is 1 upon 1 it's a gamma minus 1 multiplied with Pi, Vi and RTI. Again minus PF, VF and RTF. So NR is the common factor is equals to NR gamma minus 1 Pi minus TF. It is the final formula of work done in adiabatic process. This is the final formula of work done where N is the number of moles, R is the gas constant, gamma is the adiabatic ratio and Ti is the initial temperature of system and TF is the final temperature of system. Thank you. Welcome.